All right. Hello, class. Mr. P here. Um, it was very exciting last class. I got a knock on the door because I got a package delivered, and it was the board game Dominion. Has anyone ever played Dominion? I've heard it's really fun, so I picked it up. Um, hey, Luigi. So I'm supposed to start a science department meeting at 1 o'clock, so I'm going to get right into it because I know it takes me about 30 minutes to do these free response questions. So, what do we have today? Answer all three questions. Okay. A non-conducting thin spherical shell has a uniform surface charge density sigma on its outside surface and no charge anywhere else inside. Use Gauss's law to prove that the electric field inside the shell is zero everywhere. Describe the Gaussian surface that you would use. So basically what I would do, that's not very laborious, I like that. Usually the Gauss's law one is really laborious. What I would say is, if this is your non-conducting shell, okay, your Gaussian surface, you want to be a spherical surface just inside that, and you have basically the integral of E dot dA equals charge enclosed over epsilon naught. But you can see that this Gaussian surface doesn't enclose any charge because the charge is all in the surface of the sphere. Okay, so we have that this is equal to 0, and the only way that that can be equal to 0, you can see that, the only way the integral of something is 0 is if the thing you're integrating is 0, right? So that means that the electric field equals 0. All right. B. The charges are now redistributed so that the surface charge density is no longer uniform. Is the electric field still 0 everywhere inside the shell? All right. So it kind of depends. I think this is a really bad question because it doesn't say how is it redistributed. Is it, I'm assuming that it's not an X, if we have a, what am I trying to say here? If we have a, for example, a conductor, we know that the charge is on the surface, and if we bring in an external charge, that's going to move the charge around the surface of the conductor. But since this is non-conducting, I'm assuming that you're literally taking the charge and moving them, and then they can't move back to where they would want to go. So I'm assuming that the reason the charge is redistributed is not because of some external source. Okay, it is that. All right. And so basically, I would say that is the electric field still 0 everywhere inside the shell? I would say no. Someone arguing outside? If they're arguing, I want to listen in. Get some drama. So why would I say that? Well, basically, you would still have that the charge enclosed is 0. You would still have the charge enclosed is 0. However, there are other ways of making the integral of E dot dA equals 0. Okay? If the charge is uniformly distributed, then what that means is that the electric field has the same value everywhere on the Gaussian surface, which means that the only way you can have that integral being 0 is if the electric field equals 0, because it has the same value everywhere. Okay? But if it doesn't have the same value everywhere, you can have this integral being 0 without the electric field being identically 0 everywhere. Okay? It's kind of like there are two ways to make the area under the curve 0. You could have a function that looks like this, that has an area under the curve of 0, or you could have a function that goes up and then below, so that you have a positive and a negative. So that's what's going to be happening in part B. You're going to have, and then this is what's happening in part A. All right. Now it says, consider a small conducting sphere with a charge of plus Q whose center is at corner A of the cubical surface as shown below. For which faces of the surface, if any, is the electric flux through that face equal to 0? So the faces if we look at this picture here, the electric field is going to go away from the positive charge. Okay, so here's your positive charge, and the electric field is going to be going directly away from it. Okay, so we can actually see that the electric field is parallel to the surfaces A, B, C, D. It's also going to be parallel to A, D, E, H. And it's also going to be parallel to A, B, G, H. And if the electric field is parallel to those surfaces, then there's no flux through it. So, yeah. So these are the ones that have no flux, and I just explained why. At which corners of the surface does the electric field have the least magnitude? Those would be the corners that are farthest away from the charge. Okay, so that would be the opposite corner. All right, which would be corner F. Determine the electric field strength at the position you have indicated in part D in terms of fundamental constants, Q and L and all that stuff. Okay, so what is the distance across the diagonal of a cube? That's what we're trying to figure out here. Do you guys know the Pythagorean theorem in 3 dimensions? I don't know if you know the Pythagorean theorem in 3 dimensions, but I'm just going to say it. The Pythagorean theorem in 3 dimensions is a generalization of what it is in 2 dimensions. So in 2 dimensions, it's, s squared equals a squared plus b squared. That's in 2 dimensions. And in 3 dimensions, it's s squared equals a squared plus b squared plus c squared. So if we want to go to the opposite corner of a cube, we have to go, we have to go, say, into the page a distance L. We have to go up a distance L. And we have to go to the right a distance L. So we get L squared plus L squared plus L squared. That equals 3L squared. So that means that the distance squared across the diagonal of the cube is 3L squared. Now the electric field is KQ over R squared, which I've called S squared here. So it would be KQ over 3L squared. All right. Part F, given that 1/8 of the sphere at point A is inside the surface, calculate the electric flux through the face CDEF. So basically, we saw that 3 of the faces of the cubes get no flux. Three faces have a flux equals 0. The other faces have equal flux. Because of symmetry, so there's no intrinsic reason why one should have a different flux from the other. And so for that reason, setting up Gauss's law, E dot dA equals charge enclosed over epsilon naught. The charge enclosed, it said, is 1/8 of the entire amount of charge, so we have Q over 8 epsilon naught. And then this term is going to be the sum of 6 fluxes for each of the 6 faces of the cube. 3 of those faces get no flux, and the I'm sorry, you can't see that. And the other one is the other 3 faces share the flux equally, not easily, but equally. So we basically have that this is equal to 3 times the flux through one of the 3 faces that is getting flux. So that would be CDEF, for example. And so that would tell us that the flux through CDEF is Q over 24 epsilon naught. All right. So now we're moving on to question 2. The circuit represented above contains a 9-volt battery, a capacitor, an inductor, a resistor, and a switch with 2 positions, S1 and S2. Initially, the capacitor is uncharged and the switch is open. So here we have, it looks like we're going to have an RL and an RC circuit. In experiment 1, the switch is closed to position S1 at time t1 and left there for a long time. Calculate the value of the charge on the bottom plate of the capacitor a long time after the switch is closed. So if the switch is closed for a long time, that capacitor is going to be completely charged, and when the capacitor is completely charged, it blocks all current. So there will be no current through the 500 ohm resistor, which means that the entire voltage of the battery will be applied to the capacitor. Okay? So using Q equals CV, the charge is going to be the capacitance is 25 millifarads. That's a pretty big capacitance. And the voltage is 9 volts, which tells us that the, so 25 times 9 is going to be what, 225? 225 millicoulombs. Now, one little trick about this, I'm sure one point for this is to get the sign right. It's going to be negative charge. Why is that? Well, the positive terminal of the battery is going to push current, positive charge onto the plate of the capacitor. And so we can see that the positive terminal of the battery is connected to the top plate of the capacitor. So the top plate of the capacitor is going to have positive charge. The bottom plate is going to have negative charge. On the axes below, sketch a graph of the magnitude. So notice how they said magnitude, so now we're doing absolute value of the charge on the bottom plate of the capacitor as a function of time. On the axes, explicitly label any intercepts, asymptotes, maxima or minima, and the numerical value. Blah, blah, blah. So this is the charging of a capacitor. Okay, versus time. So I know that the charging of the capacitor looks like this. So the asymptote is going to be the value that we got in 225 millicoulombs. I feel like I'm saying millicounis almost. Millicounis millicoulombs. They almost sound the same. All right. And so basically the time t1 that they're talking about, basically the time constant is the time it takes to get within about sort of like 2/3 of the way there. So basically I'm dividing this into 3, and I know it starts here and it ends here, so 2/3 of the way would be right here. That's a time constant, and the time constant is going to be RC, which is the capacitance is 25 millifarads. So we get 25 millifarads times 500 gives us 12.5 seconds. So this would be 12.5 seconds. Okay. Part 3. On the axes below, sketch a graph of the current through the resistor as a function of time. Explicitly label any intercepts, asymptotes. So the current through the resistor as a function of time is basically going to be the derivative of this. Okay? The derivative of charge is the current. So it's going to be positive, and then it goes down to 0. Again, if I divide this into thirds, the time constant is the time it takes to go roughly to 2/3 its final value. So this would be one time constant, so that would be 12.5 seconds. How do I figure out the initial current? Well, the current, if we think about it, the capacitor starts out uncharged, which means that it has no voltage drop across it, which means at time 0, all of the voltage drop of the battery is across the resistor. So we have I equals V over R, which would equal 9 over 500. So the current is going to start out at 18 milliamps. All right. Part B. In experiment 2, the capacitor is again uncharged when the switch is closed to position at position S1 at time 0. The switch is then moved to position S2 at time t2. When the magnitude of the charge on the capacitor is 105 millicoulombs, allowing electromagnetic oscillations in the LC circuit. Okay. Wow, I didn't think LC circuits were on the AP Physics C exam, but maybe they are. All right, so part I says calculate the energy stored on the capacitor at time 0. So energy is Q squared over 2C. Why did I write the energy in that way instead of the many other ways it can be written? It's because it told me the time on the capacitor. Okay, or the charge on the capacitor. So, that gives us 105 times 10 to the minus 3. That squared divided by 2 times the capacitance, which is 25 microfarads, or millifarads, excuse me. So we have 105 times 10 to the minus 3 squared divided by 2 divided by 25 divided by 10 to the minus 3. That gives us 0.22 joules. Calculate the maximum current that will be present during the oscillations. So what I taught you was that the omega for an LC circuit is 1 over square root of LC. All right. So let's figure out what omega is. It's going to be 1 over, we know the capacitance is 25 millifarads, and the inductance is 5 henries. So that means that our omega is 25 minus 3 times 5. That means that our omega is 2.8 radians per second. So that means that the charge as a function of time across the capacitor is going to be 105 millicoulombs times cosine of 2.8 t. Okay? So we're going to use that. So part 2 says calculate the maximum current that will be present during the oscillations. Well, if I take the derivative of that, I get that the current as a function of time is 105 millicoulombs times 2.8 times negative sine of 2.8 t. So it's fairly easy to see that the maximum current would just be this expression right here, 105 times 2.8. Okay, so that would be 105 times 10 to the minus 3 times 2.8 gives the maximum current is about 0.29 amps. Part 3 says calculate the time rate of change of the current when the charge on the capacitor plate is 50 millicoulombs. So I'm not even going to solve that, but basically what I would do, what the heck, I'll solve it. So what I've got to do is I've got to set this equal to 50 millicoulombs. And then I've got to solve for time. So if I set this equal to 50 millicoulombs and I solve for time, what I'm going to get is 50 over 105 answer. So I find that the time at which we get 50 millicoulombs is about 22 seconds. All right. Oh wait, I got to do that in radians, don't I? Hang on a second. Got to convert that to radians, my bad. So that happens at 0.38 seconds. Okay? So now it's asking me basically what is I prime of 0.38, which would be 105 millicoulombs times 2.8 squared times cosine of 2.8 times 0.38. Um, 2.8 times 0.38. So that gave me I prime equals about 0.4 amps per second. All right. I think that was the laborious one for this exam. Let me see if I have any questions. All right, moving on to the last one. Oh boy. This is laborious. I can already see the picture. I know it's laborious. So this is CHL 424 part 2. And we are doing question 3. You can already see this is laborious. All right. A section of a long conducting cylinder with the inner radius A and outer radius B carries a current I naught that has uniform current density as shown in the figure above. Using Ampere's law, derive an expression for the magnitude of the magnetic field in the following regions. Well, first of all, let's figure out what the current density is. The current density is going to be current per area. So what is the area of that thingamajig? The area is going to be pi b squared minus pi a squared. So that's our current density. And let's figure out what is the current enclosed. You might recall that the current enclosed is the integral of J times 2 pi r dr. All right. J is a constant, so we just get 2 pi j times the integral of r dr from the inner radius A to whatever the outer radius is. So basically our current enclosed is going to be 2 pi times r squared minus, actually it'll just be pi times r squared times I over pi b squared minus pi a squared. And so we get that our current enclosed for r between A and B is going to be I times r squared minus a squared over b squared minus a squared. Okay, so we're going to use that. So now we get to part A. So part A I is really easy because Ampere's law says that the integral of B dot dl is equal to mu naught times the current enclosed. For that first region, we're not enclosing any current. So current enclosed is 0, which means that the magnetic field is 0 in that first region. In the second region, we're using a circular Amperian loop. So the left-hand side of Ampere's law is B times 2 pi r. And then the right-hand side, we're going to use the current enclosed that I calculated right there. So we have I times r squared minus a squared over b squared minus a squared. And so we can solve that for b. So we get b of r equals mu naught I over 2 pi r times a correction factor. Okay. And then for the third region, we're completely outside the conducting cylinder. And so for that reason, the enclosed current is just all the current, which they said is I. On the left-hand side, we get B times 2 pi 2B, because it says that it's at R equals radius 2B, so the radius of the circle is 2B. And so we can solve that and get B equals mu naught I over 4 pi B. All right. B, on the cross-sectional view of the diagram above, indicate the direction of the field at point P. So we can see that the current is into the page. So according to so if here's the center, we have a current going into the page, and here's the point P. So the magnetic field, if you use right-hand rule number 2, the magnetic field is going to be clockwise around that. So the magnetic field is going to point kind of in that direction, according to the right-hand rule. And C, the electron is at rest at point P. Describe any forces acting on the electron. I would say that the force equals 0, because there's no electric field, and the magnetic field is QVB. If there's no velocity of the electron, then there's no force. So the force is 0. Laborious. There's even more parts. I'm not even going to do part D. I'm going to say look at the answers to part D yourself, and the reason I'm saying that is because I'm supposed to start our department meeting in about 4 minutes, so I gotta go. But so I'm not going to do Discord. If you have a specific question for me, then ask me. Just send me a direct message and I'll answer it. I hope you guys have a really nice weekend, and I will talk to you on Monday. Miss you guys. Bye.